Should we start the session? So Dr. Geeta is saying yes. So I'll again remove these analysis. I'll go to the question. So I was performing descriptive statistics. After descriptive, the next question is I have to run a correlation for these variables. So if you see the continuous, first I'll see what are the continuous variable in my data set. So this pre-op, the age is a continuous variable. Then pre-op length of stay is a continuous variable. And then length of stay is a continuous variable, which is the outcome variable. So we'll see the correlation between these two. And in the correlation, generally, why do we see the correlation? Because the variables which are significant in correlation, those variables only we take as a predictor variable in our linear regression. So if I go to this analysis, regression, this is correlation matrix. Either you can do like one by one. So first I'll just do bivariate correlation. So I'll take this length of stay, which is the LOS, and age. And I'll see what is the correlation. And you just click these two variables are, let's see whether they are normally distributed or not. So for that, I'll go to the exploration and I'll see the descriptive. I'll move these two variables because if they are normally distributed, then only I can take the the Pearson's correlation. And I'll go to this QQ plot and I'll see. So age is like normally distributed, and length of hospital stay, again, if there is a confusion, you can, because why this is appearing like this, because this is a discrete data. Discrete data means like it has got a value like 0, 1, 2, something like that. That's why the residuals are behaving like this. So if you plot the density and histogram, then you see this length of stay is again, it is like a normal distribution. So then we can take this Pearson's correlation. So the value of Pearson's correlation is 0.14. It is not, it is a very mild, like not a good strength of association is not good, but it is significant. And again, I can take with LOS, I can take the preoperative LOS. So if you take preoperative LOS, the value is more than 0.3. So there is a moderate correlation. If you see here, there's a moderate correlation with a p-value significant. So I'll take both these two variable and in the correlation, and then for other categorical variable, we'll do first simple linear regression and then see what is the value of coefficient beta. And then we'll take what all variables to take. But since they have taken all variables, I'll show you how to do the regression in taking all these variables together. So I'll go to this regression and there's option of linear regression. So I'll click on this linear regression. In linear regression, what is my dependent variable? So my dependent variable is the length of hospital stay. And again, what you can do as a stepwise also. Stepwise means if you want to make more models like model 1, model 2, model 3, and model 4, you can introduce the variables one by one. So I've taken the dependent variable as LOS, and covariate I'll take. If I see the question, let me check. Since it is a simple linear regression, I'll check only one. With age, Then I'll check with preoperative length of stay, and then I'll check with the complications one by one in model 1. So I'll go to here. I will move this age. And then if you come down, here it is the block. So this is the dependent variable. This covariate box, this is for the variable, independent variable, which is continuous in nature. And this box is for the variables which are categorical in nature. And then if you will come down, you will see this is the block. So these blocks are for like, you can say it is like a stepwise or hierarchical. So in one first model, I am predicting only with age. In next, I will have age, and you can have like each independently also. So right now, since I am performing linear regression, so I'll only have this covariate as age as a covariate. And then you can see what is the intercept. Intercept is 3.87. And age is what is the beta coefficient of age? It is the 0.01. And it is significant. So if you have to make an equation, and if you see the R square, what is the R square? So the R square is like 0.02. That means 2%. It is predicting 2% variation, explaining 2% variance in the length of stay with age, taking as a predictor variable. Again, if I have to do it with a preoperative length of stay. So if I move this preoperative length of stay, then let's see what is R square. So R square is 12% here. So it is a strong predictor. And if you can recall the correlation, there also the correlation was 0.3, moderate correlation. So the beta coefficient is 0.71 in case of length of stay. So how do we interpret this beta coefficient? So we say that with each 1 unit change in this preoperative LOS, this length of stay will increase, since it is sin is plus, will increase by 0.71 days. So that we mean by that's how we interpret. Again, if you see the complications, so I am performing it one by one because it is a simple linear regression. So I will have only one predictor variable. So the next was complications. So complications, yes and no. And for complications, I have to move this to this box, since this is for the categorical variable. So I moved these complications. Again, if you see the complications, it is only explaining 1%. And it is, it is minus. That means it is taking reference as a no. If you come down, you can see for categorical, it gives you the reference. That means it is taking no complications as reference. That means people who are having complications, it is showing that the length of stay will be less, 0.48 days less as compared to the people who are not having any complications. So that's how we interpret it. In case of a categorical variable, how do we interpret? So no is the reference. So this 0.48 is the uh, beta coefficient of yes. That means people who are having complications, they will have a 0.48 less days of hospital stay in case of a surgery, after surgery. That means they will have a less stay. And this is the intercept, which is 4.4, which is the like constant. So this is, but again, this is only explaining 1%. That means it is not a good predictor. So if I see the question, I've seen with age, and I have seen with preoperative length of stay, and I have seen with the complications also. So predictor are significant, but again, except for preoperative length of stay, which is explaining like 12%, rest two are only explaining 1%, and that you can see by this R square. Now before we do that, let's see the assumptions. So assumptions, these are the 6 assumptions. So first, let's see autocorrelation. So although autocorrelation is not I mean, it is not a, it is a study design issue. And in this case, I don't expect autocorrelation, but still, as a part of academic teaching, if I just want to teach you what is autocorrelation, then you can see the value. So if the value of this Durbin Watson statistics is 2, or it is then you say that there is no autocorrelation, and it is not significant also. So there is no autocorrelation. If I click this collinearity statistics, collinearity will not be applicable here, because collinearity, when there are more than one independent variable, then we check for collinearity. Since here there is only one predictor variable, so that's why I'm not checking for it. Again, you can check for this residual plots and this QQ plot of residual. So this QQ plot of residual will show you. And right now, which variable I have? So complications. So let's see this with the pre-op LOS. Because it was 12%. So I'm taking this as example. So if I see the Asam QQ plot, it is like this. So it is showing that, yes, it is normally, again, residual plot. If you see, it gives you the fitted value at 3 discrete level. Okay. Why? Because if you see the pre-op, it is only like 0, 1, 2. And this you see like length of hospital stay with the residual. So there's no pattern. Again, why these 3 values are here? Because if you see the data, length of hospital stay is having only 3 values, 0, 1, and 2. Preoperative length of stay. If I make it as an ordinal, you can say the data point, either there is no stay or 1 stay or 2 stay. So that's why it is like 0, 1, and 2. And that's why this, because of that discrete level, it is showing all these 3 lines. Right. So this assumption, if you see this graph, I think the residuals, if you see the actual value, the variances are constant. So I can say that the homoscedasticity is met, and I can also say that it is normally distributed. Then coming to the other normality test, since I have done the QQ plot, so I will not test for normality, because it gives you the value of Shapiro-Wilk. And here the data point is like 356. So that's why I'll not check with the normality test. Now coming to Cook's distance, to see any influential point. So if you see the Cook's distance, so Cook's distance is 0. That means there's no influential point. And you can check for the individual Cook's distance also. Here you can click on predicted values also, predicted values and Cook's distance. And you go to the data and see the difference. So here you can see the actual length of hospital stay was 3 and predicted was 4.32. So if you click this residual also, I'll click this residual also. Then in the data point, it will appear and you can check. If you go to the data, so you can see the residual. This is the predicted and this is the actual. So 3 minus 4.372, it will be like 0.1372. The same data, you can see the predicted was 8. The actual was 8. And the predicted was 3.66. So the residual is 4.33. The length of hospital stay actual was 7 and predicted was 4.3. So the residual is 2.6. Can you see this? Yes? Am I making sense to all of you? Let me check the chart. So Priyanka is writing yes. What about other participants? Anju, Ajay is writing yes. So actually, you can check also in the data set. If you click this, if you click the predicted and predicted, then you can see the difference. And you can, if you click the residuals also, you can see the difference. So these are the unstandardized residual or the raw residuals. It's the difference between the predicted and actual value. And this is the Cook's distance. So Cook's distance you can see individually, and you can see like so how to check for Cook's distance. Now tell me, if I have to see the individual data point and this is the variable of Cook's distance, how will I see it? Yes, you have to guide me now. I have to see a data point where the individual data point, the Cook's distance is more than 1. How will I check that? Let me see the chart. Anyone? You can go to the descriptive and see the range. So I will just do the this thing, go to this analysis, exploration, and here in descriptive, you can have this Cook's distance variable and you can check for its range. So minimum is 0 and maximum is 0.03. So here there is no data point which is having a Cook's distance of more than 1. Otherwise, you will have to individually check. So that's a tedious task because there are 357 data points. So you can check like this. So I have like these assumptions are met, and I'm not telling you this estimated marginal mean for now. First, you do the analysis on this, and then you can click on this confidence center, this estimate. So this I have not clicked that. So this is the estimate 0.71 with 95% confidence interval, and this is the p-value. So how will you make the equation? Please, all of you write the equation. With this, as a preoperative length of hospital stay, if you have to write an equation, what will you write? Please type in the chat box. You have to write an equation using this. I will also write. So I will write this y is equal to 3.66 plus 0.71 into preoperative LOS. Yes, I think all of you written correctly. And model fit statistics, it gives you R and R square. That's okay. Like you have to tell about the model, how much is the accuracy. So this is regarding the simple linear regression equation and correlation. And regarding autocorrelation, I have told you Durbin-Watson statistics. Multicollinearity is there in the case of a multiple linear regression when there are more than one variable. So we will discuss that in the session of multiple linear regression. So if you see the assumptions check, these are the assumptions check, which normality test I have not used because this is for the lesser sample size. QQ plot, residual plot, Cook's distance, and autocorrelation. These are the assumptions. And this residual plot tells you about the linearity also. So you can check for the linearity. You can say that it is linear. So I think we can go to the breakout room and start practicing it. We have to practice the correlation and simple linear regression only with one variable. You can initially do it on age, taking age separately, and then taking the complications separately, and then preoperative length of stay in the hospital. So Anand, how many breakout rooms should be open? 27.
I'll make 4 breakout rooms, ma'am.
Okay. So one room Supriya can see, one Swapnil. And anybody else? Can I see some other question? No.
Ma'am, I have one doubt.
Yes, Dr. Namrata.
Ma'am, the third variable, that is the independent variable complication. So we got one result that complication, if present, then it is decreasing the length of stay.
Yeah.
Ma'am, how to explain that?
Actually, see, it can be like how you explain. So you have to see and you have to explain it first. It is a not a real data. I have not seen in the original article. Okay, in original article also the same has come. So it may be there, like if the people are having complications, then their health seeking is like more good, and maybe the other parameters. It is, and that's the author. This thing, I don't know whether he has explained it or not. So that will come. Maybe some interaction with people who are having, or some confounder, people who are having more complications. Some I think how we can explain that as just by seeing data, we cannot. But
Ma'am, it is a categorical variable coded as yes and no. So
yes,
it is yes is coded as 1 and no as 0. So it is like explaining all that is coded as 1 or what, ma'am?
see, this reference level you are talking now, if it is like
Yes.
this one, na? Oh, okay, no, I'll go with these categories. Here I have to see the complications. This you are saying? That its mean will be minus 0.48. That's what you are saying now, this one?
Yes, ma'am. Yes, ma'am.
So it takes no as a reference. So how you will write the interpretation? How you will write? You will
Yes,
write
ma'am. That is what I'm asking.
4.5. Okay,
So,
and plus.
so if complication is present, then it will decrease the length of stay by 0.04.
0.48. So it takes, like, if at 0, what is 0.48? 0.48 is, if it is 0, the length of stay is 4.4. That means
Okay.
in case of no complications, the length of stay is 4.4 days. And in case of complication, the length of stay will be 4.4 minus
Minus 0.48. Okay, ma'am. Got it.
with equation you can calculate. So
Okay,
this
ma'am.
actually this 0.48 is difference of stay in complications versus non-complications.
Non-complications.
It's the
Okay.
difference. So how we interpret in case of a categorical, this coefficient is the difference between your 0 and 1. That means no complications is 0 and yes complications is 1. And since it is negative, that means the same thing. People who are having complications, they have less hospital stay.
Okay, ma'am. Thank you.
And now rationally, how will you explain? That is up to author, because he have studied this. He'll have to see the other variables. Why? Because normally what we will think, that if there are complications, the length of stay will be more.
Will increase.
Yeah, but here it is coming opposite.
Yes, ma'am.
I don't know if he has explained. You can go through the article and you can see if he has explained that or not. Okay. In that case, you can see there may be some, because he has not put like interactions and all those concepts. So we may put, if some unusual of this thing is coming, you may try doing interaction. Is it the real effect, or there is some other variable which is affecting this? Okay.
Yes, ma'am. Yes, ma'am.
Then it will be more clear, because currently with one variable it is not clear. Means it is
Okay.
not explainable, rather it is clear, but we
Hmm.
cannot explain it. Maybe if you do a multiple linear, or if you perform a interaction, then you might conclude more.
Okay, ma'am. Okay.
Anybody? Anyone who is having any other doubts or one, like, have you understood in the breakout room regarding all the assumptions? Because this is the foundation for your multiple linear. And again, for other complex, we are not going to cover like many interactions, but we'll try to show you or demonstrate one interaction where that can affect your outcome, if there is an interaction, right? So if not, shall we go to the multiple linear regression? So we have seen that this equation previously also. So this multiple linear regression, this is again an extension of a simple linear regression, where your y is like a dependent variable, this y, and we explain this y in the equation of like beta 0, which is the intercept, and then beta 1 x1, beta 2 x2, beta k xk, and this is the error as a linear function. Again, now what is the purpose of these regression equations or these regression? So it can have two purpose. The one purpose can be only to see the association and the amount of association. Means like with this coefficient, you can say how these x1 and y is related. With beta 2, you can comment like how this x2 and y is related. With beta k or beta 3, you can comment how xk or y is related. So you can again see, like in correlation, you can only know strength of relationship and the direction. But amount, like if you increase or decrease one unit, or if there is a categorical variable in one reference level as compared to the non-reference level, what will be the difference? If you have to study this, for this you can use regression. Because everyone doesn't use regression for prediction. The other uses of prediction or modeling, or you are giving something a clinical decision making, something like that. So in that case also you can use the prediction. So it has got dual purpose. So now coming to this in if even if you want to see the association or the amount of association between the x and y, or if you want to predict, but there are more variables. So now in this case, if I want to predict SpO2 level of a patient, and this SpO2 is like again this partial pressure of oxygen, taking the independent variable as a age, gender, smoking status, fever, respiratory rate, and the duration of breath hold. So if these many variables are that, then I have got a multiple predictor variable, and I want to predict a continuous outcome. So all these in the linear regression, you know that one assumption is like your dependent variable should be continuous in nature. So then we make this, we go with this multiple linear regression. So what is this multiple regression? Because there are more than one predictor variable, and there are, if you see the, because all of these are linearly associated with each other, so the value of outcome variable that changes linearly with the predictor variable. So that's why it is fitting into a linear regression equation, linear equation, and it establishes a linear relationship. That's why it is known as the multiple linear regression. Again, coming to the assumptions, assumptions are almost the same, which you have learned in the simple linear, except for multi-collinearity, which I told that I will cover this in the multiple linear regression. So here again, your one dependent variable, which should be continuous in nature. Your independent variable should be more than one. which can be a nominal variable or a continuous variable. And then there should be independence of observation. This independence of observation is same as the auto correlation, which we study through Durbin-Watson statistics, and it is a study design issue. So in your case, in this case, if the dependent variable is the length of stay, generally this is not applicable, but the author has done it, and academically we are showing you. But again, if something is measurable by a lab or those errors are not there, then again, this is not always applicable as an assumption, this autocorrelation of residual. And then next is your linear assumption. This you check with the residual plot. The concept of homo or heteroskedasticity. And what is this hetero and homoskedasticity? So there is if in the residual plot, the distance, the spread of the points or the variances that is not same across the diagonal line, then you say that the data is not this assumption of homoskedasticity is not met. If there is a pattern, if there is a pattern like a funneling in or funneling out, then it is known as the heteroskedasticity. Then there is a assumption of multicollinearity. What is a multicollinearity? That we'll see. We check it with the variance inflation factor, and that is automatically calculated, and the Jamovi gives the value of this variance inflation factor. And if the value of this VIF, it should be less than 10. Then you say that there is no multicollinearity, and there should not be any unusual points. That means outliers or high leverage or highly influential point, and the data should be normally distributed. So these are the underlying assumptions of a multiple linear regression. Now, one very important thing is, like I have written here, the independent variable should be continuous or nominal. So even if there are ordinal variables in your independent variable, as an independent variable, this linear regression treats that as a nominal variable. It doesn't take into account of a proportional nature, means the ordinal nature of the 0, 1, 2. So that you should remember that in linear regression, whenever you are entering the ordinal variable as an independent variable, there also it takes it as a nominal variable. It doesn't treat it as a ordinal variable. So it still can be entered in multiple regression, but it must be treated either as a continuous variable. So why as a continuous? Because we know that if an ordinal variable has got 5 or more than 5 levels, then it behaves like a continuous variable. So either if the levels are more, 5 or more than 5, then you can treat it as like software treats it as a continuous variable, or you have to change the nature of the variable as continuous, or you can treat it like a nominal variable, but it cannot be entered as an ordinal variable. So now coming to the, if I have to perform this regression approach, I want to predict the cholesterol level and taking the age, gender, BMI and SBP as a predictor variable. So again, we say that there should be linear relationship between the dependent variable and each of the independent variable. And this all we perform on the basis of the plot, which is the residual plot, and the dependent variable and the independent variable collectively also. So that's what I said that, in case of that residual plot, I have shown you how many residual plot it is there. So if you make residual plot, it will make those many residual plot, one with the predicted one. Let's say if I move any other variable here, let's say age. And if I see the residual plot in the assumption section, this one residual plot. So how many residual plot it will make? So it will make one residual plot where the standardized residual with the, sorry, this is QQ plot. This is the residual plot. So one residual plot will be overall, that is the fitted value, with the residuals, and then the other residual plot will be the actual value of LOS and the residuals, and then the other two will be each of my independent predictor. So my independent predictor is age. If you see this here, I have age and complications. So age, and it makes the residual plot basically for the this continuous one independently. But for categorical, it makes a overall. So this you can see here, the residual plot. So that's what I wanted to tell, that the residual plot, actually, you have to see both the plot between the dependent variable and the independent variable, and the independent variable collectively, which it gives as a fitted plus the residual. So again, it is saying that to see a linear relationship exists between the dependent and independent variable collectively. So Subhapriya was asking, it is a scatter plot only. So it is a scatter plot of residual, which is the studentized residual, against the unstandardized or predicted variable. And these all are added variable. So this one, this first one. Fitted values and the residual. So this takes like overall. Fitted means like predicted one, where it is predicting the overall, and this is the residual. Then coming to, and this is the scatter plot. Again, the same concept of homo or heteroscedasticity. So this homoscedasticity, we check the variance of residual, and we check like distance and the spread of these individual data point across these diagonal line. And it is assumed that all these individual data point, they have got variances equally. That means homo means equal and skedasticity means spread. Means spread of these variances are equal across all values of the predicted one. So this line is the predicted one. If you see, this line is for the predicted one. So if you see, there is a constant spread. Means this is a constant spread. There is no funneling like this or like this, which we have seen in the previous one. So again, for heteroscedasticity, you see the scatter plot of the residual against that predicted value, and you comment on that. Then coming to another one, which is like the independence of observation or autocorrelation. I think I explained that in the simple linear regression. We have slides here also. I think it should have been there also, but again, no worries. So here in this case, if you see, this happens like if you are doing the like assessment. So just see this data set. This is in the first column, there are 20 students. And in the second column, you see that there are again marks of these 20 students. Yes. So can you see like any relationship between the marks of the previous students and the marks of the next student? Like I'll just point out, if you see the student 1, it is 70, 2, it is 75, 3 again 75. So these are 75, 76, 78. These are correlated, means almost very much similar. Again, this 5, 6, 7, you will see 82, 85, 88. Again, these 8, 9, 10, you will see that 90, 92, and 95. Again, these 15 and 16, you will see 71 and 74. So it may be okay. Even this 11, 12, you will see the 98, 100 and 98, 95. So these values are very much similar. So if you are doing something like if I'm giving marks also, you see that there is a tendency, because if it is not an objective way of marking, generally the first student we give the very less marks. And then gradually we tend to give the marks taking the first student as a like reference. So many times students, if we are given 90 or if we get 80, the next marks generally we tend to give like 80 or 79 or something like that. So this is what we mean by the correlation. Means the values or the marks here, they are correlated with each other. So how this correlation affects multiple linear regression? So basically it introduces the bias in the coefficients estimate. So the beta, which you have just seen, like the beta 1 and beta 2, it may be inaccurate. The p-values may be inaccurate, leading to the incorrect conclusion about the predictors. So that's how you should take care of this autocorrelation. But it is not a problem for all the data set. Remember, it depends on a dependent variable. So in this case, I guess length of hospital stay, it is a very objective way when the patient has reported and when he is getting discharged. So I don't think there is a problem of autocorrelation in that case. And again, that problem will not come if you are not entering the data one by one sequentially. If you are entering the data random, means case number 1 now and then after that case number 20, then again this problem of autocorrelation doesn't exist. I mean, generally that problem is not there. Now coming for the multicollinearity. What is multicollinearity? So in the case of a multiple linear regression, when I have more than one independent variable, so all independent variable, if they are in a linear relationship with each other, or they are highly correlated with each other, then again that leads to a problem of multicollinearity. Why? Because the one independent variable becomes redundant. For example, if like in a situation, if there are two or more independent variables which are highly correlated, then even if you remove one variable, it is not going to affect much. Why? Because the other variable is also giving you the same information. So your prediction or your accuracy or your model fit will not be good. So that's why this multicollinearity, it should be checked, and you should remove the variables which are highly correlated with each other. For example, if I am predicting cholesterol level of a person and I have the one value as a weight and the other variable as a BMI. So now I have derived this BMI from weight only. So if I take both these two variables as a predictor, BMI as well as weight, then these two variables will be highly correlated with each other, and there will be like linear relationship between these two linearly related, this weight and BMI. So this should not be there. Why? Because then one will be redundant and unnecessary. It will have as a beta in your equation, and it leads to the high like variance in the your predictor equation. That's why it is calculated on the basis of variance inflation factor, which is also known as the VIF. Again, if I am predicting lung capacity, and one of the factor which I am taking the physiological factor of lung capacity as an arm length. So if I'm taking both height and arm length, then you know that it is generally seen that the people who are taller, the arm length is also more. So they are closely related to each other. So if I take both these two variables, they will be there will be a problem of multicollinearity because they will be related, they will be correlated with each other. Again, if I'm predicting the heart rate and I am taking two variable, the age and resting heart rate, then I know that if I increase if the age is less, the resting heart rate is less. If the age is more, the resting heart rate is more. So there is again a multicollinearity between age and resting heart rate. So you have to remove one variable. So now how you check for the multicollinearity? Either you can inspect the correlation coefficient, or in the assumption section, it gives you the VIF value. So there are two things, tolerance and VIF. So generally we say that VIF value should be less than 10. Or you can say that the tolerance is opposite of VIF. So 1 by 10 will be 0.1. So the tolerance should be more than 0.1. But you remember VIF. Generally, VIF is most commonly reported. So the value of this VIF for that particular variable should be less than 10. So again, this is checking for the multicollinearity. So VIF is simply the reciprocal of tolerance. So if the tolerance is less than 0.1, which is the VIF of greater than 10, then you have a collinearity problem. So so remember, I always remember this. This is easy. VIF, I mean, I find it easy. VIF should be less than 10. Only remember one. Don't remember both tolerance and VIF because they are opposite to each other. Even if you remember one, you have to just remove the variable and it will help you in decision making. Now, this checking the outlier, like I said, you can have a box plot of residual, or best is to measure the Cook's distance. So these are the influential point, and we measure it using the Cook's distance. It should be less than 1. And again, you can with these scatter plot of residual, and you again run the QQ plot also of the residual. This is again the same concept of heteroscedasticity. This is we have taken, this is the SPSS output. So this is your increasing funnel, this is your decreasing funnel, this is like a fan shape. So it just tells, like, errors are not constant. The variance, it is showing you a shape. Now, so these two assumptions, so I have added just one assumption, which was the assumption of multicollinearity. Now let's see how articles report the multiple regression table. So this is one article, which is the determinants of quality of life during induction therapy in pediatric acute lymphoblastic leukemia. And they have taken like quality of life as this thing. Quality of life as a dependent variable and all other variable as an independent variable. So they have, how they have done it, they have measured the with the child health questionnaire and with the pediatric quality of life cancer version, they have collected the data and the variables they have, we will see how many variables they have taken. So these are the child health questionnaire, which inquires about these physical functioning, role limitations, bodily pain, etc. And if you see, this is your regression table. So here they have taken the scale, they have taken the determinant, and they have taken the p-value. This is the beta plus minus. This is the beta. Beta means that coefficient. And this is the standard error. And this is the R square. So they are giving like which model. So they have have different. This is the multiple linear regression analysis of the determinants associated with the child health questionnaire scores. So this child health questionnaire score, this is your dependent variable. And then if you see the determinant. So how many multiple linear regression they have run? Yes. The question is, how many tables of regression analysis are there in this? Four. So there's 1, 2, 3, and 4. These are all the scales. Scales are for child health questionnaire only. Because if you see the previous one, these are the various scales. So it is taking those as a dependent variable. So this is your dependent variable. And what are the independent variables? How many outcome variables? And how many predicted variable? You answer to this question. How many outcome variable and how many predictor variable? Yes. Outcome 4. And predictor? So predictor, it is 1, child age 2, days since diagnosis 3, gender of the child 4, treatment toxicity 5, Together, no, individually it is different. Parent is female. Days since diagnosis I have already taken. Child female I have already taken. Parent female. And that's it. So there are 7. Yes, Priyanka is right. 7 predictor and there are 4 outcome. Means separately, not together. And they have reported the p-value. So now the next question is, can we make a model equation from the values given in the table? Can we make a model equation from the values given in the table? Yes or no? What is given here? This is the beta. What is beta? Is the coefficient. This is the standard error. And this is p-value. And this is r square. Yes, Priyanka is right. Intercept is not there. So you cannot make an equation. You can tell about the effect of these individual predictor with this beta. But you cannot tell about the equation. So here their aim was to tell the association. Their aim may not be to do a prediction. Okay, so that's why they have not given an equation. Many times you will see that in regression, they don't give the equation and all those things. So maybe their aim was not like that. Again, another article, evaluation of health literacy level of hypertension patients, referred to a specialized clinic of Farsian Cardiovascular Hospital in Hamadan and its correlation with hypertension control. So here they have performed linear regression and they have performed the linear regression to examine the relationship. It was not to predict something. So remember, I have told you the uses of regression also. So regression can be performed for understanding the relationship, the amount of relationship also between the two variables, and it can also be used as a prediction model. So in this case, their aim was to examine the relationship between the health literacy and hypertension control, moderating the effect of other factors. So if you see this, they have analyzed this relationship with the health literacy. So which is the dependent variable here? Yes. What is the dependent variable in this case? All of you please write in the chat box. Farzana, you have written, can't we calculate A and B using software? You can, but you need a raw data. You don't have that data. If you have the data, yes, definitely you can calculate. It gives an intercept. You can ask, then you will have to ask about for the data and then you can calculate. Otherwise, from this table, you cannot. So yes, Priyanka, Geeta and Dr. Sunil are right. It is the health literacy. And if you see, they have used these variables like age, gender, and if they have given something in the bracket, that means they have taken male as a reference. So they are giving you the regression coefficient for females, the duration of disease, smoking, family history of hypertension. So whatever they are giving, it's the difference between the family history and no family history, physical activity and no physical activity. So you have to understand the reference level on your own. The reference will be the opposite of that. And then this family history of heart disease. And this is the average arterial blood pressure. So I don't know why they have written like 25 minus 0. The regression coefficient, two things. Both they have written. I don't know. Why they have written like this? 30 point. There is some typo error. This minus, I think by mistake, they have just inserted. And then this is the standard error and this is the significance. So you see that these variables are not significant. If you see the significance, it is the physical activity and the gender, age. So they have written like multiple regression on the relationship between the health literacy and hypertension control, and demography and disease variable showed that after moderating the variable of age, gender, duration of disease, this, health literacy was still significantly associated with the all areas of hypertension control. So this they have taken like hypertension control score. and they have taken like self, these are the like continuous. So that's why they have given the regression coefficient like this. These are the maybe must be measured on some scale, and these are the continuous outcome. So all of these were significant. They're saying that these behaviors were significant. Now coming to another article, which is the factor associated with the delayed diagnosis of breast cancer in Northeast Thailand. So there they have analyzed the factors affecting the doctor's delay by linear regression of the delay in days on the risk factor, knowledge, attitude, and practice. So you can see. Then what is the dependent variable here? Result of linear regression of patient delay in breast cancer. So the dependent variable is the delay in breast cancer diagnosis, which is a continuous outcome. And the independent or the predictor variables are the family income, previous breast symptoms, and smoking status. So if you see, like they have written this number, like this is the categorical one they have written. How many number and percentage in this column. This I'm only showing you, you can have a multiple way how you want to present your table. So these are all of these are categorical predictor, and this is giving you like these three values in these three levels, and then this is your previous breast symptoms, yes and no number. This is the mean delay, and if you see, they have not given the coefficient. If you see what they have given, they have only given the value, the p value. And what is univariate and multivariate? So in univariate, they have entered this variable only as a simple linear regression. And in multivariate, they have entered all the variables. So that's why the p-value is different. And they have written like adjusted for two variables. The other two variables are like these breast symptoms and smoking. So here they have not given the value of beta. That coefficient is not here. Even the standard error is not here. They have only given the p-value. But we encourage, at least you should give the value of beta. Because without that, it will not be possible to interpret that beta coefficient is necessary, and you should give it with the 95% confidence interval. Am I making myself clear with all these tables, what is missing, how the other people have reported? Yes or no? Farzana is saying yes. Geeta is saying yes. Okay. Now this is another. Priyanka is again saying yes, Namrata. Okay, thank you so much. So now coming to another thing. If you see, this is the linear regression analysis of doctor delay in breast cancer. Okay, so this is the another model. This is the same. They have taken like other. Okay, this is the continuation of that same. Here they have adjusted for separate variable. Multivariate A is like they've adjusted for occupation, previous symptoms, self-treatment, distance, and stage of pathological diagnosis. And in model 2, they have taken the travel time of hospital. But again, they've given only the p-value. Another article is like pregnancy outcome variable and associated factors in different nationalities living in Kuwait. And here you can say like they have taken various dependent variable. So here they are changing the dependent variable also. So in the first model, they have taken like body weight as a dependent variable, and predictor variable is like this pregnancy weight. Then this MH is what? Let me see. Birth weight, head circumference. MH is maternal height, maternal hemoglobin, and gestation age. So this is maternal height, this is gender. And this gender is probably of the gender of the child. And this is the regression coefficient. Similarly, here they have given the constant, the intercept they have given. And then these are the regression coefficient. This is the 95% CI. And they have given the R square also. So if you see this R square, this is 40%. So this is explaining the maximum this thing. But here the dependent variable is different. Here it is the body, this is the birth weight. This is the head circumference, crown heel length, and this is the placental weight. So again, 4 different dependent variable with a different predictor variable is same, I think, in all these. Except in the last one, it is only the gestational age. Another article, gender differences in psychosocial predictors of attitude towards reporting child sexual abuse in the United Kingdom. So they have performed univariate regression analysis in order to assess whether age, family cohesion, social support, masculinity, callous affect, and interpersonal manipulation were significantly associated with attitude towards reporting the child sexual abuse. So again, their aim is not to predict something. Are you getting my point? So regression is not always for prediction. They are performing regression because they want to see whether these factors are significantly associated with the attitude towards these child sexual abuse. And then they have performed it. So it is not always that you have to predict something, right? By these, just I want to emphasize that. So this here they have performed this regression analysis. Predicting the factors, attitude towards reporting child sexual abuse. So this child sexual, then what is the dependent variable here? Yes, all of you please write. What is the dependent variable here? Yes, so Dr. Suresh is right. Priyanka is right, child sexual abuse. And this age, family cohesion, social support, they have taken like beta and they have written like star, like this is giving the p-value with the 95% confidence interval and the standard error. And they have also given separately, yes, Dr. Namrata, right, for the males and females, this beta. So they have done a like in the full sample also and separately for males and females also. Another article, risk factors for impaired pulmonary functions and cardiorespiratory fitness in very long-term adult survivors of childhood acute lymphoblastic leukemia after treatment with chemotherapy only. And here they have again performed the multiple linear regression. And you can just see how they have written. The independent variable entered, if you see there, the independent variable, they entered into the regression model where those were hypothesized up a priori for biological or clinical reason. That means it is often asked like what variable you will enter. So either you can decide it a priori. A priori means from the review of literature, you know that these variables are important, or you can again see its significance level in the univariate analysis. Univariate analysis means you will perform a simple linear regression and you will see a p-value. So even if the p-value is up till 0.2, you can take those variable in the as a predictor variable in the multiple linear regression. Am I making myself clear how you will decide on the which variable you will take as a predictor variable? So either it can be decided a priori. A priori means as a clinician, you think that these variables are important for me. Or not only as a model, you want to see like relationship between those two variables. Then you can take it. Or when you are doing the calculation in the simple linear regression, you see the p-value of each and every variable and you take only those variable which have the p-value of more than like less than 0.2. You instead of 0.05, you increase the cutoff up till 0.2. The same thing we do in the logistic regression also. So same concept is applicable here as well. Even if any predictor variable, if it is not significant, means the p-value is more than 0.2, but as a clinician you think that that should be there, or you want to see the the strength of relationship or the amount of relationship, how it is changing, then also you can have this. Okay. So this is the univariable and multivariable linear regression. And you can see this is the predicted, this is the continuous dependent variable with all these female gender, age at diagnosis, follow-up, BMI, smoking, left ventricular ejection fraction, etc. This is again serum level of interleukin 6, 10. So Pallavi's writing is that 0.2 is no, you can decide. Ideally, you can use the combination of both. A priori, you fix few variables and then few you see while you are doing the analysis. But I said that even if it is more than 0.2, then also if your aim is just to see the relationship between the two, you can still take that variable. But generally, it is said that you should take variable which is because if in the univariate, if it univariable, if it is showing up till 0.2, if it is more than 0.2, in multiple linear regression, there are no chances that this variable will become significant predictor. That's generally seen that if the value of independent, the p-value of your predictor variable in case of a simple linear regression is up till 0.2, then only there are chances that in an adjusted analysis it will become significant. Okay, so that's why it is generally said. It is in all the literature you will see that it's the cutoff which is said. But again, if there are many predictor variables, that's the maximum cutoff what we have decided. If you say that no, you will take only those variables where the p-value is up till 0.05, that is up to you. Because if you want to reduce the number of variables, many times what happens, there are many predictor variables which are significant. In that case, how will you decide? So in that case, you may reduce your cutoff, and instead of 0.2, you may keep it as 0.05. Am I making myself clear, Pallavi? Unit chart. Okay, thank you. Then coming to another article, which is the serum level of interleukin 6, 10, and 13 before and after treatment of classic Hodgkin's lymphoma. So they have taken the clinical and lab data were used in 2 models of multiple linear regression to predict serum level of interleukin 6 and 10. Before performing statistical test, value of cytokines level were transformed to their Napierian logarithm to normalize their distribution. So they have transformed the dependent variable here. Remember, I said that there should be your continuous variable or the dependent variables should be normally distributed. Or if the data, if the heteroscedasticity, remember I said that if the heteroscedasticity or the homoscedasticity assumption was not met, then also you need to transform. So here they have transformed the variable and they have used this Napierian logarithm. You can use the log 10 transformation also. And they have tested the collinearity also. Using the chi-square, the model was checked for linearity, independence, and normality. They've used sigma stat, some other, and they have given like dependent variable and then predictor variable, coefficient, and standard error. But here the dependent variable, it is the transformed variable. Again, this is one like effect of air pollution on mortality and clinico-pathological features of esophageal cancer. So here they have taken it is like an association. So probably the mean concentration they have taken in all 17 cities and esophageal cancer mortality. So in model 1, they have performed linear regression analysis with the combination of mean concentration of PM10, SO2 and NO2. And esophageal cancer mortality rate were considered as a dependent variable. So maybe mortality, they are taking it as a rate. So it is a continuous variable as a dependent variable. And mean concentration was considered as an independent variable. You can see they have written collinearity diagnostic was made in each model and there was no collinearity between the independent variable. You can see. So this multiple collinearity, this assumption is very important. Then we'll go to, so now another concept of estimated marginal mean. So I'll tell it, but before that, let me demo the multiple linear regression. And then I'll tell this estimated marginal mean, if time permits. No, as possible. Okay. So I will demonstrate this and then we'll start tomorrow. First with the breakout room, you will practice and then I'll explain the other concepts. So let me see the question. So this is the multiple linear regression. To take the LOS as a dependent variable, age, gender, pre-op, this length of hospital stay, complication at the time of diagnosis, and comorbidities. So I will now, in this case, I will go one by one. What do I mean by one by one? Means I will not enter all these variables together. So what I assume that I have used that, how I have to do, you check each one by one. So I will use this age and see the p-value. So this age is significant. P-value is significant. So I have taken age. Then I'll move. I will take pre-op. Pre-op was also significant. We have seen that. And then you can take other like complications. So complications, I'll move here. So here I am doing, I have no, a priori, there are many. But let's say I have decided I will take all. But even then, if I want to use the combination of both, so you can see here that this p-value is again, it is more than 0.05. So this is not significant. It is 0.0. Yes, but if there are many variables, then you can keep it at 0.05 also. But if you have kept the cutoff up till 0.2, then you will take these complications also. So this is also significant. Then complicated diagnosis, you can take it. So what I'm doing, I'm checking one by one. What all variables will I take? So it is 0.16, this one. So up till 0.2 I have to take, so this I will take. Then again, author has taken the other, this thing also, like this comorbidity, he has defined like any comorbidity, then he will take it as a comorbidity, yes. So again, this is significant 0.05, I'll take this also. So similarly, assume that I have checked all the variables and all the variables are like a priori also fixed that these are important for me. And in the p-value also, I have seen that the value is up till 0.2, the p-value. So I have decided to take. Now I will, if I have to make a model, how will I go? So we make these model one by one. So first I'll enter this, let's say gender. I'll see the length of stay gender wise. So I have entered this and then you come down and here there are blocks. So you keep on adding blocks. So that will show you many models like adjusted model, and this is known as the hierarchical. We are going to build the model one by one, not all the variables together. So this is gender. Now I'll add a new block here and then I will, along with gender, I have moved this age also here. So now this table will show me, if you see the output, this shows the model fit measure. So with the first model, the R square is 1%. With the second model, R square has increased to 3%. So this tells you the model comparison. That means if you go from 1 to 2, this R square increases up till 2%. And from here, you can see like this is your table. And if you like click this will show you like if you click this model 1, it will give you only in gender. If you click on this model 2, it give you both gender and age. Similarly, if you want to have more variables. For that, you go down and create one block. So I have created one block, add one block, and then probably I will have this pre-op LOS. So pre-op LOS I have moved here. And now you see from model 2 to model 3, the change in R square is 13%. So this is a very significant percentage. So from model 2 to model 3, the change in R square is 13%. Similarly, you can have few more, like let's say I've added this comorbidities. So comorbidities, no. So for that, what you have to do, you first create a new block. So I have added a new block, and then I will enter the comorbidities here. So this is my model 4. So with this, you can see the comparison. This table will show you the difference in R square from model 1 to 2, 2 to 3, and 3 to 4. And this change in R square, you can see from this value, change in R square. So again, there's no significant changes in R square, only 1%. So till now, my third model is the best model. Again, you can add a new block. And you can enter like instead of comorbidities, again, you can write this as a complications. So I'm including complications also. So this will give you the last model. And again, it is increasing 2%, not a much increase in R square. And this is how will you interpret this? So this estimate or this tells you the difference. So this 0.33 tells you the difference of length of stay between male and female. Means male has got a higher stay as compared to female, because here the female is the reference. Similarly, if like comorbidity, if there is a comorbidity, the length of stay is more, 0.42. In case of complications, we have seen, now you will see that the values are different. There it was 0.47. If you are doing the like only simple linear regression, here it is 0.73. Means if there are complications, the length of hospital stay was like 0.73 less. The difference, the difference between the yes and no was 0.73. And if like you wish to see the other model, if from this drop down, you can see the other model. So this is how you keep on adding variable and seeing like where you can see a change in R square. Either you can do this way, or there's another way also. If you don't want to do like this, then you can enter all the variables together here. But again, in that case, you will not be able to see. If I like just remove all these blocks, here again in this, I'll have to move age, pre-op, all these variables together. Then pre-op, then comorbidities and complications. So in that case, there won't be those many models. There will be only one model, or there will be only one equation, and you can see it gives you like this is the intercept, and these are all the. So this way, the R square is 0.19 or the 19%. And again, assumption check. Oh, I forgot to check for the collinearity. You click on the collinearity statistics, because that is important. You have to see whether all the variables you can take or not. So this is collinearity statistics. And you see that all the variables, they have got a VIF value less than 10. It is like 1.01. So they are, the problem of multi-collinearity is not here. So you can take all the variables. Any variable showing the value of VIF more than 10, in that case, you have to drop that variable as a predictor variable. In this article also, if you see the table, they've given the tolerance and VIF. And here, their value of tolerance is like, it is 0.9 VIF, but it is less than 10. Okay, yes. So this was tolerance, this was VIF. So all the values was less than 10. So they have given a separate table for these multicollinearity. This is the graph, standardized residual versus standardized predicted value. They have given this also. And they've given the normality, this one also, QQ plot.
Ma'am, can we fill the colors in this scatter plot dots?
That option in Jamovie, it is not there. I don't know, they have used some stat color. It has got this thing. Color, I think it is not. Plot theme. Let me see. Let me see if I change blue. Let me see if it gives some colorful. Otherwise, from here you can explore. I don't know. I have tried few times. It is descriptive message. It is not giving. Maybe in Dr. Shamshad is saying in descriptive it gives. This is the plot. You can keep on trying, like plot theme also, like love SPSS minimal default. These are black and white headlay, and color palette also these. But many times it works. Sometimes it doesn't. Like in this case, it is not working. And then this they have given the QQ plot also. This one. The assumption. So basically this article is just to show they have given each and everything. Even the formula also they have written like adjusted R square and all, which is, I mean, it's not needed always from your end. You can give the values. You can go through this article. And this is the model summary. So they have given the standardized and unstandardized. So what is unstandardized? Unstandardized means each variable taken separately as a simple linear regression, and standardized is like when they have taken all variables together. No. This is coefficient. Standardized coefficient is like in this option. No, I'm sorry. Here you will see there's a standardized coefficient, and if you click this standardized estimate and confidence interval, this is not related to variable. They have performed multiple linear regression, but the standardized estimates are when you like this beta also there is a standardized value. So if you see here, this is the estimate of your unstandardized. This is unstandardized. And this is your standardized, this one. So both these two they have given here. Generally, that use adjusted and unadjusted. Here, standardized and unstandardized. And then they have written the discussion. So have you understood? Yes or no? So Pallavi is writing yes. Okay. So if you have understood up till this point, then I think we can conclude today's session. If there are questions, we can take it. Otherwise, we will start. Again, we'll restart with this session, the breakout room activity, tomorrow morning at 10 o'clock. And then we'll discuss, because I need to discuss few more concepts, which is the estimated marginal mean, the plot of estimated marginal mean, and interactions, which we'll discuss tomorrow. Is it okay? Okay, if it is okay, then we can conclude today's session. We'll share the recording. So Farzana is saying almost. Okay, no worries. By tomorrow, maybe when we'll repeat these concepts many times, then you will be able to understand.
Ma'am, I have a question regarding my PhD. So should I ask now or should I reach out to some another time?
If we discuss, because tomorrow we will have time. So
Okay, ma'am.
we'll discuss it tomorrow.
Sure, ma'am.
Is it related to regression or some other concepts?
No, not related to regression, but it's related to another concept.
Oh, then we may discuss after this workshop, means we will conclude, we'll have a talk with you.
Sure, ma'am. Sure.
Okay, Farzana.